All right, so we have been talking about quantum field theories, which simply put are the modern theories of what the most fundamental particles are in nature and how they behave and how to describe the interactions they have with one another. One of the things that we talked about very early on at the beginning of this conversation was that the quest to figure out what the elementary things are in the universe is a very long one. The idea of atoms dates back to ancient Greece. The modern idea of atoms dates to the 1700s, 1800s. There was a time that we thought these things that we see in the periodic table were elementary. They're the simplest objects that existed. That's why it's called the periodic table of the elements. But we discovered in the dawn of the 20th century, the very first few decades of the 20th century, that these are not elementary, that the elements are actually made up of smaller, more fundamental things. And the interesting part of this story is that there were hints of that based on the patterns of the relationships in the periodic table. If you know anything about the history of this table, they're not just arranged haphazardly. They're arranged by weight, so hydrogen's the lightest, and helium's twice as heavy, and carbon is 3 times as heavy, and the weights of carbon, nitrogen, and oxygen per atom are related to one another. And the vertical columns, they're related by their chemical properties. All of these things in the first column form similar sorts of chemical bonds. You got H2O, or Na2O, or K2O, for example. All the things in the last column don't form any chemical bonds at all. The noble gases, helium, neon, and argon. So the vertical columns are based on recognizing a pattern that some of the chemical elements reacted with one another in similar ways. And those patterns were hints to a substructure. The reason the masses follow a certain pattern is because the mass depends on how many particles are in the nucleus. The reason carbon has a mass of 12 and oxygen has a mass of 18 is that carbon has 6 protons and 6 neutrons, and oxygen has 8 protons and 8 neutrons. It's not an accident. The pattern had meaning. The reason that hydrogen and lithium and sodium combine chemically in similar ways to one another is they all have one outer valence electron, and it's that outer valence electron that determines how you react chemically with other things. So the patterns that we saw inherent in the properties of the chemical elements were hints to a deeper structure. The reason I bring that up is because we're going to see that happen again 100 years later. We talked about the fact that protons and neutrons and the nucleus of an atom were thought to be fundamental. Protons, neutrons, and electrons make up all atoms, so we thought for a while, okay, we've got it. From, say, 1899 to 1930 or so, our picture of the structure of matter was pretty simple. You got protons, neutrons, electrons, those are the fundamental particles. But over the next couple of decades, we started discovering more fundamental particles. We already talked about the electron and the muon and the neutrino, but we also started discovering heavy particles that were similar to the proton. The first thing we discovered is that the proton, just like the electron, has an antiparticle called the positron. The proton has an antiparticle. It's called an antiproton. It's not called a negatron, which I feel like it should be. If the positive electron is called a positron, then a negative proton should be called a negatron. It's not. It's called an antiproton. The neutron also has an antiparticle, which is the antineutron. You might say, well, if the neutron is neutral, what is its antiparticle? If it has no charge, how can you have anti-no charge? We'll get to that in a little bit. But then in the 1940s, we discovered particles that were similar to but lighter than the proton. These are called pions. There's a neutral pion, there's a positive pion, and there's a negative pion. We also discovered a particle called the kaon, which is a little bit heavier than those. In the 1950s, we discovered the lambda. We also discovered around here a particle called the delta. In the 1960s, we discovered the omega minus and the Xi particle. In the early 70s, we discovered the J psi. Why is it called the J psi? Why does it have 2 different names? Because 2 different groups who discovered it at the same time gave it 2 different names, and since it was a tie, we just decided to call it by both names, which is really ridiculous. It's one particle with 2 names, the J psi. The upsilon, discovered in 1979. So from just before 1950 until the mid-1980s, we were discovering not just a few of these elementary particles, these heavy particles like the proton and neutron. We were discovering dozens of them, maybe even 100 or so of them. Well, could there really be 100 different elementary particles? This seems like kind of a mess, and it was. The situation became very similar to the situation with the periodic table. Maybe these things aren't elementary at all. Maybe the patterns we see of their masses and their charges and their various properties are a hint that there's some level of structure below the proton and the neutron and all of its complicated zoo of little friends. This theory came to fruition in the late 1960s through the efforts of Murray Gell-Mann and others. And the idea was, because there seemed to be many different combinations of these heavy particles with different masses, maybe the proton is not fundamental. Maybe there are smaller particles inside of a proton. Those particles wind up being called quarks. There are two main kinds of quarks in the world around us of everyday life. There's the up quark, which has a charge of plus 2/3 of a fundamental charge, plus 2/3 the charge of an electron. And there's the down quark, which has a charge of minus 1/3 the charge of an electron. So we used to think the electron's charge was the smallest charge that anything can have. That's not true. Quarks have smaller charge than an electron. And if you look at a proton, it has an up, and a down. What does that make its charge? 2/3 plus 2/3 minus 1/3, that's 3/3, that's 1. Plus 1 is the charge of a proton. So it works. What about a neutron? What does a neutron have to have inside it? Well, a neutron has no charge. So whatever is inside a neutron has to add to 0. Well, if you take an up, which has a charge of plus 2/3, and a down, the total charge is 0. So a neutron has an up, a down, and a down. And 2/3 plus minus 1/3 plus minus 1/3 equals 0. So you could explain the pattern of charges of the proton and neutron with three particles, two kinds of particles, 3 each inside of a neutron. And it turns out we could explain the properties of all these other particles, pions and kaons and lambdas and deltas and psis and upsilons, by combining together these quarks in different ways. So just like we discovered that the periodic table is not fundamental, there's really protons and neutrons in there that determine the masses of those atoms. Proton and neutron aren't fundamental. There are really little particles inside there determining the mass and the properties and the charges of those particles as well. So if there is a force that holds the atom together, it holds a proton to the electron, it's the force of electrical attraction, there must be some force that holds the proton and neutron together, some new force that's different from electrical charge. And it has to be different from electrical charge because the two up quarks on a proton both have positive electrical charge, plus 2/3 and plus 2/3. What do they want to do? They want to push each other apart, right? Like charged things electrically want to repel one another. But there is some other force, some other attractive force that holds the proton together. How do we think about that force? Well, when thinking about electrical forces, we know that in the world around us, most of the time, things have the same number of protons and neutrons. We say that's electrically neutral, right? Protons have a positive charge, electrons have a negative charge. And if you have the same number of pluses and minuses, that adds to 0. Now, these terms, plus and minus, don't really mean anything. You've heard them all your life. You've heard that there are positive and negative charges. What does that mean? That just means there's this property, electrical charge, that comes in two types, and the two types cancel each other out. Well, proton and neutron have 3 things inside that have to cancel each other out to make this whole thing stable. So we need some new kind of charge. It's not electrical charge, it's something else. And its property has to be that 3 of them add together to make nothing. Now, the analogy of positive and negative is 2 things that mathematically add together to make nothing. What's the analogy of 3 things that add together to make nothing? The analogy that scientists came up with is, well, it's like how red, green, and blue light add together to make white. Right? If you have a red light and a blue light and a green light and you add them all together, you get no color, sort of. I mean, is white a color? I don't know. But red plus green plus blue equals neutral, equals colorless. So we called the names of these charges that quarks have red, green, and blue. We call it color charge. They're not really red and green and blue, even though I can't help myself coloring them red and green and blue when I make these presentations. Color for quarks has nothing to do with colors of things. It is a name that we gave to their charges to remind ourselves that it takes 3 of them to add to nothing. Okay, so another word for these types of charge is flavors. Electric charge comes in 2 flavors. We name them plus and minus. Gravity, the force of gravity, is always attractive. It comes in 1 flavor, mass. Mass causes gravitational attraction. So gravity has 1 flavor, electricity has 2 flavors, plus and minus, and the color force, the strong force in the nucleus, has 3 flavors, red, green, and blue. They don't have anything to do with real colors. So because this force is stronger than the electrical repulsion between the quarks, we call this the strong nuclear force. And the charge of the strong nuclear force comes in 3 flavors, 3 varieties that are nicknamed red, green, and blue. Okay? Now, how does this force work? We said that for electrical attraction and repulsion, we can think of that repulsion between 2 electrons as being created by the exchange of particles that push the 2 electrons apart. And those particles are photons of light, quanta, individual chunks of energy of the electromagnetic field. Well, we need a force responsible for attracting 2 quarks together. And so we came up with a model for a force that pulls them together. And we came up with a name for the particles. Those particles are called gluons. Gluons are the particles that quarks exchange that creates the strong force, just like photons are the particles that charged particles exchange to create the electromagnetic force. The name gluon is meaningful because you can think of the strong force as being like glue. Glue is very strong, but it only works when the 2 things are very close to one another. Imagine you had 2 magnets, and you took the 2 north poles of the magnets and you tried to push them together, and it's very hard because they want to repel one another, right? Now imagine putting glue on both the magnets and putting the magnets together. They're repelling, but you touch them until the glue sticks, and they're still repelling each other magnetically, but the glue is stronger than the repulsion. That is how to think about what 2 quarks are doing inside of a proton. The 2 up quarks want to push each other apart. And a neutron, the 2 down quarks want to push each other apart. But when you get them very close, the strong force is stronger than that repulsion. And the gluons are the glue that holds quarks together inside of protons and neutrons and all these other exotic particles like pions and kaons and whatever that are not important to us in this class. Why is the strong force so strong? Why is it stronger than electrical repulsion? The reason is that in electrical repulsion, photons of light carry the electrical force. They're responsible for that force, but they don't feel the electrical force. If you shine a flashlight past a magnet, the magnet doesn't affect the photons. It doesn't bend the light. Photons don't feel electricity. They don't have their own electric charge. But gluons do have color charge. A gluon does feel the strong force. Gluons can be exchanged between 2 quarks, but they can also be exchanged between 2 gluons. So when you have 2 quarks exchanging gluons with one another, while those gluons are being exchanged, they're exchanging gluons with the other gluons, which creates a force between the gluons, which makes the whole thing stronger. The electromagnetic force, the force of electrical, you know this from magnets. When magnets are far apart, the magnetic force gets weak, right? Electrical charge, if you have, you take your socks out of the dryer and they're stuck to your sweater and you take the socks off and they're electrically attracting one another, repelling one another. When you move them far apart, that attraction gets smaller. Electrical forces decrease with distance. The strong force actually increases with distance. The farther apart you try to pull 2 quarks, the more the gluons can exchange gluons with other gluons, and that makes the force stronger. The reason we draw gluons like a little spring is because just like a spring pulls stronger the stronger you pull them apart, gluons pull the quarks harder the further you pull them apart. This is one reason why we have never seen, well, maybe until the late 1990s, well, early 2000s or so. We've never seen a quark by itself. Our theory that protons and neutrons and lambdas and psis and kaons and pions, the theory that they have quarks inside, is based on studying the patterns of their masses and charges and other properties. We've never seen just a quark sitting by itself in the lab. Why? Because the only way to do that would be to take one out of a proton. What would happen if I banged this proton with something and tried to knock this quark out? If I pulled the quark out, there would be more time for its gluons to interact with the other gluons, and that force would get stronger and stronger and stronger, and it would pluck it right back in. What would happen if I pulled it really hard? The bigger the distance between this quark and the other quarks, the more gluons are exchanged. The more the gluons exchange gluons with the other gluons, the more energy is in this gluon glue. And from Einstein's equals mc squared, once you get enough energy, that energy can be converted into mass. So what happens is that energy just makes a new quark and antiquark. One of the quark pops back in here, and the other quark leaves with this quark, and you get a little double pair of quarks that wanders off. So anytime we try to get a quark out of a proton or a neutron, we just make more quarks. And we make it from the energy of this strong gluon field. So we never see quarks by themselves, which is interesting. So this is a different kind of force from electricity, but it's based on the same idea of exchanging particles with one another. These particles are just different than photons. It's a whole different field, a whole different quantum of energy of that field, a whole different particle. That is the tiniest bit of interaction of that gluon field, that QCD field. QCD is the name we give this theory of exchanging gluons with color charge. It stands for quantum chromodynamics. How do we know quantum chromodynamics is right? Well, it predicts the behaviors and properties of all these heavy particles, like the proton and the neutron and all of its heavier friends and all of its lighter friends. It predicts their properties very well. So we're fairly confident that QCD is an accurate, precise, at least useful theory of the structure of these particles. So protons and neutrons are made of up quarks, plus 2/3 charge, down quarks, minus 1/3 charge. They all have their own color charge as well. As we banged more and more particles together with more and more energy in our particle accelerators, we made heavier and heavier and heavier particles that could not be explained with up and down quarks alone. So we discovered that there are heavier families of quarks. There are the charm quark and the strange quark, which are just heavier versions of the up and the down. And finally, there are the top quark and the bottom quark. The history of the top quark is actually really, really interesting. For a long, long time, we only knew about these 5 quarks. Okay, up, down, charm, strange, and bottom. And we looked at this pattern and said, there are 3 minus 1/3 quarks, the down, the strange, and the bottom, but only 2 plus 2/3 charged quarks. That can't be right. There must be one that we haven't found yet. And we built a really big particle accelerator to go looking for the last missing quark. So the top quark was predicted before we ever went and found a particle with a top quark inside of it. It's a success story for quantum field theories. The pattern didn't make any sense without it, and so we went out and tried to see if it was there, and it was there. So 6 kinds of quarks: up, down, charm, strange, top, bottom, heavier and heavier and heavier. This pattern should look familiar from what we've talked about before. Okay? We talked about the fact that the electron has its 2 little heavier friends, the muon and the tau. That the ordinary everyday neutrino, the electron neutrino, has its 2 little heavier friends, the muon neutrino and the tau neutrino. So we have this picture of sort of 3 different kinds of matter particles: charged leptons, like the electron; neutral leptons, like the neutrino; and quarks. Some of them feel electricity. Some of them feel electricity and the strong force. Some of them only feel the weak force. By the way, electrons and quarks also feel the weak force, but the neutrinos only feel the weak force and no other forces. So weak and electric, strong, weak, and electric. Interesting. But notice that they all come in three, we call them families. The light one, up, down, electron, neutrino. The heavier ones, charm, strange, muon, neutrino. And then some really heavy ones, the top quark, the bottom quark, the tau lepton, and the tau neutrino. And then there are the force particles, the particles that are exchanged between particles that create the forces. The electromagnetic force, caused by the exchange of photons of light. The weak force, caused by the exchange of these heavy, weak bosons, the W and Z bosons. And the color force, the strong nuclear force, caused by the exchange of these gluons with their own kind of charge, called the color charge. And that's it. Almost. That is all the particles we know about in nature. It's interesting, right? That we've been able to figure out that everything in nature is made up of how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 particles. They all have antiparticles, by the way, too. There's an anti-up quark and an anti-down quark and a positron and an anti-strange and anti-tau neutrino. So is it 12 or is it 24? That depends if you think of antiparticles as being different particles or just the same particle with a different, I don't know. It's either 12 or 24 particles, and that's a small number, right? Everything in the universe is just made of combinations of these 12 particles. And every interaction between them is governed by these three forces: the electromagnetic force, the weak force, and the strong force. So the reason this is called the Standard Model is because it seems to explain all of the interactions we see between particles in nature. That's a big achievement. I have a book about the Standard Model. It's called The Theory of Almost Everything. Why almost everything? What's missing from this picture? A couple of things. First of all, there's a particle I didn't talk about called the Higgs boson, which was actually discovered fairly recently and has to do with why particles have mass. The electron and the muon and the tau have different masses. The electron is like 115 times lighter than the muon, and the tau is like 1,200 times heavier than the electron. One of the big lingering questions about the Standard Model is the whys. Why do the particles have these particular masses? Why do they have these particular charges? Why are there three families of all of these things instead of 4 or 5 or 1? We don't know. There are some interesting patterns, right? The electron, then heavier, then heavier. The up quark, then heavier, then heavier. The difference in charge between an electron and a neutrino is 1. Electron has a charge of -1. Neutrino has a charge of nothing. 1 minus nothing is 1. The difference in charge between an up quark and a down quark is 1. Plus 2/3 to minus 1/3 is 1. Why? Is there a reason for that? We don't know. There are no whys to be found in the Standard Model. No whys for how many particles there are, what their masses are, why certain ones feel certain forces and not others, and how strongly they feel the forces that they feel, how strong they couple to the photon, the weak boson, and the gluon. How strong is each of these interactions? We don't know why. We can measure it. We know what these strengths are. We know what these masses are. We know what their charges are, but there's no reason. Maybe there is no reason. Maybe these are just the properties that these particles have, and there's no deeper level of understanding. That's a little unsatisfactory. Right? So one of the big unanswered questions in physics right now is there a why that explains why these particles have the properties they have? And is there a why that explains why these three forces exist and they have the properties they have and they have the strengths that they have in our universe? Right now that question is unanswered. The other thing that's missing from this picture is gravity. I said that all the interactions that particles have with one another are governed by these quantum field theories where they exchange particles. Electricity, 2 electrons exchange photons. The weak interaction, two neutrinos exchange Z bosons. The strong nuclear reaction, two quarks exchange gluons. What about gravity? All of these particles have mass and they all feel gravity. Why isn't it in the standard model? Because we already have a theory of gravity, and it has nothing to do with little particles being exchanged between things. Our theory of gravity is Einstein's theory of general relativity, which says that what causes gravity is the geometry of space-time, the curvature of space. We've talked about this when we talked about black holes. What does that mean? Does that mean there are three forces in nature that work one way and one force that works completely differently? Maybe. Or maybe not. Just like we can view these forces as an exchange of the smallest piece of energy you can have in the electromagnetic field or the QCD field. Maybe there's a smallest amount of gravity you can have. Maybe there's a smallest amount of space-time curvature you can have. Maybe, just like a photon is the smallest amount of electromagnetic energy, maybe there's something called a graviton, which is the smallest amount of space-time field energy. The problem is, we don't have any theory for that works. We don't have a quantum theory of gravity. Okay? Our theory of gravity is completely separate from the standard model. One of the reasons that this state of affairs has happened is because the force of gravity is very weak. The strongest force in nature is the strong nuclear force. The next strongest is the electromagnetic force. The next strongest is the weak force. And the weakest force in nature is not the weak force. The weakest force in nature is gravity. If you take two electrons and you put them a nanometer apart, and you ask, what's the electrical force between them? The electrical force wants to repel two electrons, right? But gravity wants to attract the two electrons. So electricity pushes them apart, gravity pulls them together. How do those two forces compare together? For an electron, a nanometer apart. It turns out that the electrical repulsion is something like 10 to the 40th times stronger. That's a 1 with 40 zeros. That's a trillion, that's a 1,000 trillion. 36, three more. It's 10,000 trillion times weaker. Gravity is 10,000 trillion times weaker than electricity for two electrons. That means when we're doing experiments in particle accelerators and examining the forces that electrons and protons and neutrinos and pions and kaons and whatever, we examine the forces that they're exerting on one another. The force of gravity is so weak that we don't have to consider it. It's so many decimal points down, 30, 40 decimal points down from the strong force and the weak force and the electrical force, that in a particle accelerator we can just pretend gravity doesn't exist. So none of our quantum theories of how particles interact ever needed to talk about gravity. What needs to talk about gravity? We need to talk about gravity when you've got a star and a planet and another star and they're exerting gravitational forces on it and they have masses of trillions of kilograms. So gravity was generated to talk about really big things in a big region of space, exerting forces on one another. These theories were developed to talk about little tiny things in a little tiny region of space, exerting forces on one another. So it shouldn't be surprising that these two theories arose independently and they have nothing to do with each other. I mentioned this a few times in some other videos, I think. Where does that leave us? That leaves us in a situation with our unanswered questions. Why these particles? Why these properties? Why these forces? Is it just an accident or is there a reason for it? Why does gravity work differently from the other forces, or does it? Could we have one theory that was about space-time and about little fields with quantized exchanges of energy? When you hear scientists talking about a unified theory, or a grand unified theory, or a super unified theory, or a supersymmetry theory, or a theory of everything, or string theory, or M theory. What all these things are ways of talking about the question of, can we create a single theoretical framework that encompasses these quantum theories of really tiny stuff and the theory of big, massive things curving space-time. We don't know if that's possible yet. String theory, that you may have heard of, is an example of an attempt to do such a thing. And we've been trying for 20, 30 years and haven't really gotten very far. String theory isn't really a theory yet. It's basically just a bunch of mathematical ideas that physicists have for a way that we might be able to do this, but no one has done it. There's also theories like loop quantum gravity, which I don't really know anything about. But I know what it is. It's an attempt to create a single theory that does both of these things. It deals with little tiny things and deals with things with a lot of mass. What does this have to do with astronomy? Try to remind us of where we're going with this. What is a black hole? What happens in a black hole? The mass of a whole star collapses down to the size of an atom or smaller, and you have something that's very massive and very tiny. And what does physics tell us happens? Physics tells us nonsense. It tells us that this thing disappears but still has mass, has a finite mass but infinitesimally zero volume, and that's nonsense. That's what a singularity is. What happens if we look back closer and closer and closer to the Big Bang? You've got the whole mass of the universe that at one point in the past was squished into the size of a galaxy. And then earlier than that, it was squished into the size of a solar system. And then earlier than that, it was squished inside to the size of a star. Then earlier than that, the whole mass of the universe was squished into the size of a baseball. Then earlier than that, the mass of the whole universe would have been squeezed into the size of an atom. And then you would have something that obeys the subatomic quantum rules of quantum field theories, but is also as massive as the whole universe and is all of space-time in that tiny, tiny volume. Can we talk about how nature behaved when all of space-time was the size of a baseball? Maybe. And the question is, how far back can we go? As we go back, we will eventually hit a brick wall. And the brick wall we hit is that place where our quantum theories and our theories of gravity don't play nice with each other anymore. That's why physicists are looking for a unified theory. It's to answer these unanswered why questions. Why are the properties of the particles what they are? But it's also to see if we can talk about what happens in nature when massive objects like collapsing stars and the whole universe get down to the size of what the universe would have been like a nanosecond after the Big Bang. So that's why we're talking about quantum field theories. What do we do next? I might record a little video about trying to explain why quantum mechanics and gravity don't get along with one another. What are the different assumptions behind quantum field theories and gravity that make them incompatible? I might record a little video about string theory. I'm not sure that's in your best interest. What I do want to record right at the very end will be a lecture about the unanswered questions in physics and the unanswered questions in astronomy and what we are doing today to try to answer those questions. So that's where we're headed in the next couple of videos.